suffering. Now it is recording. All right. Okay, so we have this, we're starting on basically limits. And limit, what is limit? Limit is the value that the function gets to. So limit is the value that a function, let's say a function f of x gets to when the values of x in some interval on the x-axis goes to, or let's say approaches, let's call that a here. So it never really gets to, so we're going to call this approaches. So limit is the value that a function f of x approaches when the values of x in some interval on, let's say, x-axis approaches a. So is the value that the function f of x approaches on the y-axis. So we have the x-axis here, we have the y-axis here. Okay, all right. So now what's happening? We're going to make the graph, and the function. So this is 1, 2, 3, 4, and we have 1, 2, 3, and 5 and 6, and this thing goes right there. Okay, so here is our function f of x, and just make it slightly nicer looking. So we have our function f of x, okay, and we could even and in fact this graph, this function happened to be this specific one. And it doesn't matter, right? So just generically, so we have this guy here. This is the graph of that function. And now let's go back to what the limit. Limit is the value that a function f of x approaches on the y-axis when the values of x in some interval on x-axis approaches a. So where are we approaching on the y-axis? Anybody? If I'm coming down from the top, and when I'm coming up from the bottom here, so a is 2, and the limit equals maybe, so let's figure that out. So Jake, as I go up, and come down in some interval when the x values so the question is, when we get closer and closer to 2, what is the what value does the function approach? When the domain values, when x approaches 2, what does the function approach, Mr. Jake?
It approaches 4.
All right, and this is, of course, just make you speak up, and so you're now awake. Very good, which you were. Okay, should I do anything else? We need arrows here as well. Okay, and I have a dot here. Let's say it doesn't matter if it's defined here. That means 2 is defined here. What does that mean? That means that if I put 2 in the function is defined and its value is 4. Okay, and so this is the value of the function at 2, and the limit of f of x at 2 is also 4. Okay, so limit of the function at 2 is also 4. Of course, we write it like this. When we talk about functions, we go limit of f of x equals, or we can say the function approaches the value of 4, and that is its limit as x approaches 2. Okay, and so that is usually how we state the above one. Now, what if x was not defined at 2, and there was this giant hole, and this function, let's pretend it's some really weird function, at 2 it gives us the value of 6. So at 2 it is 6. Okay, does it still have a limit, Mr. Jake?
I guess, yeah, it would, right?
Yes, it's a trick question. So we're not concerned about what happens exactly at 2, but near 2. So we are concerned about so what we're really concerned about, let's write that down. We want to know that, oh, 1 second. Is that who is, I hear some noises. No, okay, I'm just getting confused. So what we want to know about a function is how it behaves near a number x in the domain so near x, not at x, as in x equals not equal. So if near, for instance, near a number, let's say a, we are concerned about near the number a. So if a2 is our a here, so it doesn't matter if it's defined or not, as long as the function is defined over here and here. So one of the things we can say is that this function f of x is defined on, let's call this, and I'm going to put a here, equals to, is defined on this interval here. So we have an interval on the line, and the interval goes a plus delta and a minus delta. So within the delta distance, all the values of x, if you pop it into the function, you will get values for f. If I pop in and those values, these are the ones that we are interested in, right here. And Jake, is that you or is that?
I mean, I can mute myself.
You can. I'm like, yeah, it can't be Tristan, so I'm kind of confused. Okay, it's some random noises. Okay, so I think I'm gonna. So this is the key thing here: near A, not at A. Okay, let's move on. Any questions? Does this? So the whole idea is, how is a function behaving near some point, and does it? And if it does approach some number, that is its limit. So the limit is the value that a function f of x approaches on y-axis when values of x in some interval on the x-axis approaches 2 or a. Okay, I'm going to delete this, and well, and in fact, let's do one last thing before I delete this whole thing. If there is an interval here on which all the x's, so the interval starts here from here to here. In this interval, all the x values are defined for the function f of x, which means that if we plug these x values into the function, we will get values of the function, and then those values of the function will be, so the number 4 is our limit. And usually we call this L, and then perhaps we need this to be L plus epsilon. We use delta down here, and then this number here would be L minus epsilon. So when we are near A, where all the x's are defined, this will then fall, and we get a line here. This is getting really messy, but it falls within. Okay, we're gonna do a little bit more of this. So this is just Jake, this probably doesn't make any sense, right? What I just did? You're supposed to say no, yes. Okay, so let's keep going here. Okay, so forget about all this. We're gonna go again and start thinking about what is this business of limit. Limit is the value that a function approaches when in the domain x approaches some value, and that is the central value. Let's see. Okay. Oh, yeah. Trying to figure out the best way to make sense of this. So let's see if this might be a good way. Yeah. Okay. That didn't really work. Okay. Let's do. let's do this thing. This is again intuitive. And okay. So if you have a notation like this, and this is from another book in calculus. Always have trouble with the spelling. Okay, so this is from Swokowski, so Kowalski or something like that. And let's look at, so here's a chart and I'm writing the chart here again, notation. And the notation is the limit notation. And it says as the function x, the limit notation goes as x goes to a, yeah, that's a, then the function goes to this value called L. So as x in the domain goes to the value of a, right, then the function near a, so as the values of the function go towards a from the left and the right, the value of the function goes to L. And that is called the limit of the function. So now I'm going to write so this is our graph here, our table. And this is all intuitive. If you see a notation like that, its intuitive meaning is and I'm going to write out what the book says. We can make f of x as close to L as desired. Okay, so we can make f of x, and this will all make sense in a little bit, but once I actually get to the definition and all of that. So if you run into this limit notation, limit of f of x as x goes to a is L, what this is saying is supposedly we can make f of x as close to L as desired by choosing x sufficiently close to a, sufficiently close to a, and x doesn't need to be, the function doesn't need to be defined at a, x doesn't have to equal a. Okay. Okay. This should not make any sense to you guys. Okay, Jake? If it is, then whoa, that is super cool. All right, now I'm going to draw the graph. And okay, need to get the graph right. We have goes like that. And we have a point A here. And our L is going to be right here. Okay. Now, as x's go towards, as x takes on values from the left and the right towards A, but never really A, the values of the function go from the f of x from the right and the left go towards L. And L is better expressed as this height here. Okay, and we have, and the interval in which all of this is happening is right here. So if we take, oh, so this would be, let me move this in here. So this, let's move this a little bit here. So this would be A minus delta and A plus delta. So we have an interval that this function f of x is defined. That interval is so this is the interval on which f of x is defined. And as in this interval, the values of x go towards A or approach A, the values of the function approach L. And so we have, so every time x gets closer and closer, values of the function will fall in here between, let's move this here, between L plus epsilon and L minus epsilon. So let's write that down here. And so here what will happen is as we get an x here and let's say another x here, the values of the function, so this one for instance, will fall here. We'll get a fx here and maybe another one. And all the fx values that we get as x approaches A are within epsilon distance of L, the limit. So the interval on which f of x is defined as x goes to A on this interval A minus delta and A plus delta, the values f of x fall within epsilon distance of the limit L, that is the values of fx, the values fx's fall within epsilon distance or fall in and in this thing here, in this interval, L plus L minus epsilon and L plus epsilon. So we have a interval here. And we have a interval going on here. A minus delta and A plus delta. Whoa, okay. So, all right, so this still probably perhaps, and what happens here is, what we're doing is we're replacing as x goes to a with, so we replace x goes to a or approaches a with x is in this interval, a minus delta and a plus delta. And then so as x goes to a, we replace that notion with x is within this interval. And we replace this notion of f of x goes to this value of function L with f of x's fall within L minus delta and L plus delta. And so what we have done is we have what we are really trying to achieve is this, replacing phrases like approaches, near with notions of distance, as in x is within delta distance of a. So that is number one. And number two, we want to replace f of x is, so this is within epsilon distance of L. So we want to replace approaches, gets to, all of that with this kind of language. Okay, so Jake, tell me, how bad is this?
Honestly,
Yeah.
it's not bad.
It's not bad?
I think this, yeah, because this is kind of in line with what we've kind of done with the last couple
Before.
modules. Yeah, so
Okay.
it's not like a completely new set of material.
Okay, and you've seen epsilon, delta, and all of that, and okay, very good. And then because there are a couple of things going on, I'm also using the interval, right, notation, and I'm also using the idea of delta distance and epsilon distance, right, from A and from yeah, no, that will work. Okay, all right. So if you're fine, let's keep going. Unless Liliana wants to say something. Okay, so we did that. All right, let's move on.
I understand.
You do? Yeah, you're good?
Yeah,
Okay.
I think he's right. It's pretty similar to what we've already gone through, so I'm not lost.
You're not lost. Excellent. Okay. And that's the plan, is I'm going to do sequences and other things before we get to this stuff so that it makes more sense. All right. Very good, Liliana. Let's keep going. And I want to do something. What should we do first? Okay. Actually, yeah, this does. Okay. Hopefully it will all work out. And we still haven't got to the actual book yet. So let's write. All right, so let's do this. Okay, I am still worried about how to present this thing. Okay, I think we can do some more swasks. Oh, okay, cool. All right, so let's write some definitions. of a limit from the same textbook as before, this guy. And then again, Liliana and Jake stop me. And hopefully, if this works out, I'll post this on the YouTube channel. So again, what happens in calculus is as the function is moving towards somewhere because of the domain, the input is changing, we want to know where it's going to end up. So anyways, and this thing is very crucial for calculus. So we're still on our Swokowski, or whatever his name is, and let's write, and this is definition of limit of a function. So definition of a limit of a function, and this definition is, sorry, I needed to put, so let's say definition, and this definition is 2.4 from this book here. Okay, and the book says let, so this is the statement of the definition. It says let a function f be defined on an open interval containing a. Okay, so I'm going to, so we have a function f. Let a function f be defined on an open interval containing a. So let's draw that out, right? So we have our y-axis and we have our x-axis here. Or y-axis is also called the f of x. And the definition says that let the function f, so here is our function, let's say, here is our function f of x, or function f, and it is defined as in, for these values centered on a, so our open interval is, we're gonna call it a minus a small positive number delta and a plus a small positive number delta. So this is our interval right here, a minus delta and a plus delta. And now, so let's read this again. Let a function f be defined on an open interval. We got our open interval, and it says that any value from this open interval of a, any value of x from this open interval, except for the value a, and it's going to say that the function is, if I take this x, within this, let's say the function ends right here. Let's do this here. If I took a value of x is right here, let's say this is 1, is the function defined at 1 for our function f, Mr. Jake?
It would be, right?
No, look at the dotted line. It doesn't
Oh,
hit
sorry,
the,
it's outside of the,
yes,
it would-
outside of the,
yes,
exactly, outside of the open interval,
right.
okay?
Outside of
And
the-
in fact, is the function defined for this number?
No.
No, because it's not included in the interval, right? It's an open interval. If the interval was this,
Yeah, then it'd be like.
then the function would be defined. If we had a closed interval, then this would be, the function would have a value at this point, okay? All right. Very good. This is better, right?
Yeah.
I think
yeah.
after because it's the preamble is done. Now let's keep going. And then it says, so let a function f be defined on an open interval containing a, I'm gonna switch these out with, okay. And then the definition says except possibly, because it could be defined and or it might not be, it doesn't matter, at a itself. Okay. And then it says so, and let L and let L, let's see. Oh, so, okay, and then let L be a real number. So let's put L right here. And as A goes up, let's put this back here. So either A has the value L or it doesn't. So let's keep it to where it doesn't have the value L here. Let's keep that here, and then the function might have a value up there. Okay, so it says the statement the limit of the function f of x equals L, that is, the function approaches or gets close to the value L when x approaches A. And then and therefore we can, now we're going to bring in all our, so let's do this here before we do that. So this is L plus epsilon, this is L minus epsilon. Any x here, if you plug it into the formula for the function, the f of x will fall here. All the f of x will fall right here. So any value of x that we choose within this interval and plug it into the function, it will be defined, and it will fall within these guys, within the open interval on the y-axis. Okay, and the book goes on to say this means, so this notation means that for every epsilon greater than 0, and this is a part of the consequent, not consequent, sorry, antecedent. So this is one of the assumptions. It is one of the givens. Oh, okay. All right, so that is better. All right, so means that for every epsilon, a positive number epsilon, there is a delta greater than 0. And so there is means, so what's going on is given a epsilon, given this interval, given the interval on the y-axis, if we have an interval on the y-axis, we will be able to, there will exist, so this is an existence theorem, there will exist another interval on the x-axis. So let me write here. So this guy here is for every epsilon that defines. So for every epsilon that for all epsilon, this is upside down A, which means all, for all epsilon, given any epsilon, big or small, any epsilon defined any epsilon that defines an open interval on the y-axis containing the limit value of the function, right? Limit is the value of f, limit L. So this whole thing, so means that for every epsilon greater than 0, as in for all epsilon, all these epsilons define an open interval on y-axis containing the limit L, there will exist a delta on the x-axis, and delta will define yet another open interval containing A. And I didn't put the interval here, but it's this guy here. So let me put it here. L minus epsilon and L plus epsilon. Okay, and then actually, so those were just asides. When you see this, means that for every delta greater than 0, there is a, for every epsilon greater than 0, there is a delta greater than 0. And so then this gets translated as if, so we take this guy here, and this becomes so x approaches a becomes the distance of all x's from a is within delta distance, or the distance between all the x's on the x-axis from the center point A is smaller than this positive number, and none of the x's can be equal to A. That is, x minus A is not equal to 0. So let's write this. This is x approaches A, right? This thing gets translated into that all the x's are, what did I say? All the x's are, all the x's distance from the center point A is less than delta. Okay, Mr. Jake, what do you think? Do you get that?
Yeah,
okay,
yeah,
so this is vague, and this is rigorous. This is vague, this is rigorous. So this is the notation that opens up into an if-then statement, like a theorem. And so it goes, if, so we just translated that. So the limit of f of x equals L as x goes to A. What does x goes to A means? All the values near A that are within delta distance of A. Okay, then the book goes on to say, if this is true, then, so I'm going to delete this business. Take this kind of off, so it's cleaner. And now I'm going to translate this bit here. And that goes, all the values of, if we take all the values near the center point A, if we take all the values, if we look at all the values of x near A within delta distance of A, then when we plug these values into the formula of the function f, we are going to get values of function that are strictly, that are within, so values of f will be, their distance from L will be exactly less than epsilon. Okay, all right, and yeah, and then this is, and this value right here, sitting here, is called the limit. Okay, so that is, do I need to do anything else here? We'll skip this. And okay, so let's do a proof. Yeah, okay. And then before we do that, there's a line L+1 that, and then there's a line here that is, so these are the horizontal lines. These two. So let's clear this up here. So on our graph, I'm trying not to make it too messy, but L plus epsilon and L minus epsilon are two horizontal lines. And then coming up, and then these two here, let's use this. These two vertical lines that I just drew in blue, A minus epsilon and delta and A plus delta are two vertical lines. And between the horizontal lines and the vertical lines, we get this box here. And that box defines the portion of the function f, the graph f, where as we get closer and closer to the value of the center point value a, the value of the function approaches its center L, the limit. Okay, all right. So with those two in our heads, let's do a quick little theorem because it's just too cute not to do that. All right, so. And oh yeah, one last thing. This definition that you wrote is called famously epsilon delta definition of limit. Or we could also write it like this: epsilon delta definition of limit of a function. Okay, so of a function. Okay.